Esto se titula La crisis. El mundo está en crisis, más crisis, ¿cuál crisis? Zodíaco enfermo de Acuario hasta Piscis. El mundo está en crisis. Los hermanos Lehman sin broncas ni guerra dejaron en llanta la vida en la tierra. Todos en la llaga, todos boca abajo. Se van al infierno, salud y trabajo. Son los energúmenos dueños del dinero, turbios creadores de este innoble agujero. Queda en este party para desayuno del recién nacido siglo XXI. El mundo está en crisis, más crisis, ¿cuál crisis? De tantos Guernicas que hoy ninguno dice. El mundo está en crisis. Canción prostituta de vil aritmética, con publicidades, basura profética, que abuenan a incautos, nosotros tontitos, boludos en cuotas, románticos fritos, y el triste que cobra pensión cibernética, y algún ministerio con cáncer en la ética, y un sordo proyecto que siempre es el mismo, con su falso rótulo de espiritualismo, en la multimedia con su anonimato, patanes de patrias que duran un rato, dan sordos balances de templos nefastos, plegarias de ingresos, mercados y gastos, un mundo cual vil malandrín que hace guita, como única fórmula de ciencia maldita, y el profe y la monja, y el juez y el pionero, y el sabio y la madre son un puro cero. El mundo está en crisis, más crisis, ¿cuál crisis? Siniestro y mediocre pus de apocalipsis. El mundo está en crisis. El bursátil suda y arde en autoagravios, torturando a filo de cheques sus labios, buscando en su mente algún buen fusible que alivie el presagio de esta fija horrible. Los irresponsables del credo egoísta serán ante Dios igual que terroristas, y un santo en pelotas murmura en la esquina: qué bien que me abriga la gorra de espinas. El mundo está en crisis, más crisis, ¿cuál crisis? El mundo está en crisis, más crisis, ¿cuál crisis? La verdad en crisis y su horror profundo, y los dioses ciegos, crisis de otro mundo.
Okay, in this segment what we're going to do, we're going to take a look at why Nukiyama is having some difficulties with his experiment. And remember, that was where he's doing a power controlled experiment, not a temperature controlled experiment, when he was getting the boiling curve. And the reason is there is a thing called a burnout, or what we also call boiling crisis. And so that's what we're going to talk about in this segment. So as it turns out, in many different applications, we only have control over the heat flux. We don't have control over the excess temperature between the surface and the saturated liquid that the boiling is taking place in. And so if you recall the boiling curve, and what we're going to do, we're just going to sketch it out here again. So we have QS double prime, and then we have our excess temperature down on the horizontal axis. We came up, we hit the onset of nuclear boiling, we come up and through, we go through the critical heat flux, we come down to the Leidenfrost, and then we go up into the film regime. If you were doing the experiment like Nukiyama was doing, and this point here is C, this is where we called it the critical heat flux. And why did we call it the critical heat flux? Well, that's what we're going to answer right now. So if you were doing the experiment that Nukiyama was doing, and remember Nukiyama, what he had is he had a pool, he had a wire coming through it, so he was sending a current through the wire. He was measuring the delta V here. We know power is equal to Q, which is equal to IV. And so he was able to control the current, and he was able to measure the voltage, and that enabled him to control the power. He had no way of controlling the wire temperature itself. That he would have obtained through Ohm's law, V equals IR, and then he would use R is equal to the voltage divided by the current, and then he would know that the temperature of the wire was, actually let me write it this way, the resistance of the wire was a function of the temperature of the wire, and you can get a relationship and then determine from the resistance measurement what the wire temperature would be. So Nukiyama was doing his experiment, he's going along happy, collecting data, he's moving up this, he sees bubbles starting to occur as he increases the heat flux, he's coming along, he gets here and he is continuing. Now remember, he's not controlling this, he is controlling the heat flux. So when you get here, and if you move up a little bit, where are you going to go? Well, the only place you're going to go is you're going to shoot across to here, and then you're going to continue going up there, but, now let's go down here. Remember that this is T wall minus T sat. Well, T sat is a constant, so in order to jump all the way to the right, like he did here, to come out to this point, the wall temperature, the wire temperature, jumps up really, really quickly. And it can get incredibly high, and it can get so high that what happens is your wire melts and it disappears. And that is what happened to poor Nukiyama when he was doing this experiment. He would do it, and the wire would burn out. And I bet he was very, very frustrated and thinking, what the heck is going on? And so anyways, that is the burnout or the boiling crisis. Now, Nukiyama was very persistent, and I'll tell you how he got around this problem in a moment. But let me make a comment. So the surface temperature can jump from C to E, and I didn't put E here, but this is E, and this was C. So what happens is that we can jump from C to E. When we look at our boiling curve, we can quickly go from C all the way up to E, and this can exceed the melting point temperature of the wire. And that's why it's sometimes called the burnout point or the boiling crisis. You do not want to operate your system there because if you're exceeding the melting point of the material, it will melt down, and that happens with nuclear reactors, and it can also happen with electric resistance heating devices like Nukiyama was using. So how did Nukiyama get around this? Well, what he did is he changed the wire. He originally used a nichrome wire. Okay. So he went from nichrome, originally using nichrome with a melting point of 1500, and then he went to platinum. That had a melting point of 2045. That enabled him to go above E and collect data up in this region here. Now you might be wondering, how was the rest of the boiling curve determined between the critical heat flux point and the Leidenfrost point down here, which we call D? Well, the way that you do that, you do a temperature controlled experiment. And an example of a temperature controlled experiment is if you have a pipe and you put a vapor in it that's going through a phase change. So if you change the pressure in this pipe, you can vary the saturation pressure. That would be what you would do for your wire. And then you have your pool out here. So you're going to have two saturation temperatures, but you have two different liquids in there. You would have one vapor going to liquid on the inside and then your water out here. And with that, you can then control independently what the wall temperature would be based on the pressure. So you'd vary the pressure inside here, which would drive the saturation pressure wherever you wanted, and you could then control the wall temperature. And that is how the rest of the boiling curve data was eventually collected. So anyways, that is the boiling curve, many different aspects of it, looking at the physics. What we're going to be doing in the next lecture, we're going to be looking into the correlations that you can use in order to estimate. Remember, we're after the convective heat transfer coefficient. So we're after H, and we're going to be looking at the relationships that enable us to determine what the value of H would be when we have boiling heat transfer.